So we talked about kinetic molecular theory, which is explains what's going on. Now we're going to talk about some gas laws, which just say this is what happens. The pressure of a gas depends in part on its volume. If we keep the temperature and the amount of gas the same, the pressure will increase if we decrease the volume, and it will decrease if we increase the volume. This happens in a bicycle pump. When you pull up on the handle of the bicycle pump, there's a one-way valve down here that will allow air to come in. When I pull up on this, I'm increasing the volume inside the pump. That causes the pressure of the gas to decrease. Because of that decrease in pressure, air will flow into the pump. When I push down on the handle, now I am decreasing the volume. I'm squishing it together, which puts pressure on it and increases the pressure. That then forces the air out into the tire. The relationships between gas properties are described by gas laws. And I'm just going to go ahead and add something in here. The properties we're talking about are pressure, temperature, volume, and amount of gas. So we're going to talk about pressure, volume, and temperature first. There's mathematical relationships between the pressure, the temperature, and the volume of a gas. Robert Boyle, back in the 1600s, studied the relationship between volume and pressure of a gas. One of the neat things about gases is that there's a lot of things you can do that don't require a lot of technology. This was the 1600s. They didn't know what electricity was. They didn't know what atoms were. And yet they did some pretty cool stuff studying gases. So when we look at Boyle's law, we're talking about a situation where the temperature is not changing and the amount of the gas is not changing. So Boyle's law tells us that the volume of a gas and its pressure are inversely related or proportional. So that means if the volume increases, the pressure decreases. If the volume decreases, the pressure increases. That's an inverse proportionality. And this is the sort of equipment he used to study this. So here we have a glass tube. It's called a J tube because it's shaped like a J. This side is closed and the other side is open, and it's got mercury in it. If both ends of this tube were open, the mercury would go to the bottom and the sides, the heights of mercury on each side would be equal, right? Because we've got equal amount of pressure going down. But this is closed on one side. There's a gas in here. And because these levels of mercury are not equal, we can tell that the pressure inside is not the same as the pressure outside. The pressure of the gas inside pushing down on this mercury is greater than the pressure outside because it's pushing the mercury up this way. And we can measure that with a ruler, low tech. We can just measure this distance with a ruler in millimeters and see what the difference in pressure is, millimeters of mercury. So what he did is he was messing with the pressure of the gas and measuring the volume. He could change the pressure by increasing the amount of mercury. Just pour some more mercury in there. Pour mercury in there and it causes the mercury over here to come up and squeeze the gas, but the pressure is still measured by the difference in these two column heights. Now that difference in pressure is greater and the volume is smaller. And so he graphed this. Here's volume as a function of pressure. So as the pressure increases, the volume decreases. We can explain this with kinetic molecular theory. Here we have a container with 10 gas particles in it. Here's the pressure gauge telling us the pressure is 1 atmosphere, the volume is 1 liter. If we increase the weight on here and press this cylinder down and cut the volume in half, we see that the pressure doubles. What are the particles doing? Well, these particles are still the same number of particles. They're moving at the same speed, but now they're in a smaller container. They're going to run into the sides more often, and so the pressure is going to go up. So this is the mathematical expression of Boyle's law, and we're going to learn how to do calculations. If we know the pressure and volume at one set of conditions, and we know the pressure or the volume at the other set of conditions, we can calculate what the missing value is. So what we're going to do is we're going to learn how to use a table to organize this information, because we're dealing with 2 pressures and 2 volumes, and it's easy to get them mixed up. So the first thing to do is always to read the question all the way through. A cylinder equipped with a movable piston has an applied pressure of 3 atmospheres, a volume of 5.0 liters. What is the pressure of the cylinder if the volume is decreased to 2.0 liters? So we're going to make a table. We have 2 sets of conditions here. We have the first and the second, so we'll just call them 1 and 2. We'll set this up and then we'll read the question again and pick out the numbers. So we read through and we see pressure of 3 atmospheres. That's a number, let's write it down. Apparently that's more difficult than it sounds. 3.0 atmospheres. Always write the units. That is the pressure. So I'm going to label that column pressure, and I'm only going to write pressure in that column. The question here is telling me pressure of, so that's nice. If they didn't say pressure of, I should be able to tell from the unit. Atmosphere is a unit of pressure. The next number we come to is 5.0 liters. So I'm going to write that over here. 5.0 liters. That is volume. So I'm going to label that column volume. We can tell that these 2 numbers go together. It says applied pressure and volume. Those 2 are together in the problem. And then it's asking, what is the pressure if the volume is decreased? So this is volume after something has happened. So I'm going to put that in the second row. Now in my table, I've got all the numbers from the problem, and I see that I have an empty square. That corresponds to the question. What is the pressure? That is a pressure that's missing. This is column P, it's row 2, so I'm going to call that P2. So now I've identified P1, V1, V2, and I can use this equation up here to solve for the missing thing. P1, V1 equals P2, V2. We need to be able to rearrange equations. So there is some algebra in this chapter. I am looking for P2, this guy. So I'm just going to make him yellow in this equation so that we can kind of focus on what we're doing here. Some students like to plug the numbers in and then solve. It's not a good idea. There's just so many things that can go wrong. It's really better to rearrange the equation, solve for the variable that you need, and then stick the numbers in. You'll get the answer correct more often. So rearranging an equation. I have P2 times V2. I need to get rid of V2. I need it to go away. I'm going to do that by dividing. If I divide by V2, when we divide by something that is the same, V2 over V2 is 1, right? When we multiply by 1, it doesn't change anything. So we say those cancel out. but this is an equality. It's like a balance beam, not a balance beam, a teeter-totter. It's like a teeter-totter. So if I do this to one side, if I want this to stay balanced, I have to do the same thing to the other side. So whatever I do to one side, I have to do to the other side. So I divided the right side by V2. I have to divide the left side by V2 in order for it to still be equal. So now I'm just going to rewrite this because it's kind of messy looking up there. P2 is equal to P1 V1 over V2. Just be careful when you copy that you get the numbers in the right places. It's really easy to get the 1s and 2s backwards, and then your answer is wrong. So there's my equation. It's always a good idea to write this out and then to show it with all the numbers written in. I know that some of you can rearrange an equation like this without writing anything down. That's awesome. But then write down the rearranged equation. Because if something goes wrong, you can come back and look at it and figure out what went wrong. So now I'm just going to plug these numbers in. P1 is 3.0 atmospheres, and V1 is 5.0 liters, and V2 is 2.0 liters. I always want to pay attention to my units. I have liters over liters. Those are going to cancel out. That's a good sign. There will be some problems, especially in the homework, where they might give you milliliter and liter, or gallon and liter, or cubic meters or something. They'll give you two different units. And when you come over here and they don't cancel out, that's when you know, oh, wait a minute, I need to convert one to the other. So they will throw things like that at you. I'm sorry. So here I've got 3 times 5 divided by 2, 7.5. And the unit is atmosphere. Always a good idea to ask yourself if the answer makes sense. Look what happened to the volume. The volume went from 5 to 2. The volume goes down. If we squeeze a balloon into a smaller space, do we expect the pressure to go up or down? Up. So we expect the pressure to be higher than 3, and it is. So that's a good sign. The most common problem that people have is they'll get these pairs backwards. And so sometimes you can catch a mistake that way. Any questions?